for example, data stream, and also you have some kind of image data set, and from, the data you have, how can we detect the anomaly detections? That's what we have discussed yesterday, right? So I gave you several examples, like a support vector machine to, one class classification problems, and some very well-known algorithms like K and N, right? And also some we had discussed about, statistical analysis for detecting the anomaly detection. So if you cannot understand more clearly about this kind of methods, you can ask the question whenever you want. Okay, during my talk, during the break, I will be happy to discuss and explain again. Okay, so please ask the question. Don't hesitate. Okay, don't be shy. Please ask the question. Today, I want to talk about more details about the multiple time series. So this is one of my, in my research group, in my lab, I have several students who solve this problem, since 2 or 3 years ago. We have been focusing on multivariate time series data, and how can we detect the anomalies from multiple time series, okay? So I'm going to talk about this. And then this is the first part for today. And second part, so I'm going to show you some examples, applications. So how can we apply our ideas, our system, for the applications. Okay, so the first example is the traffic congestion detection. If you have a lot of, if you go to the street, there are a lot of motorbike, a lot of car. So how can we manage this kind of traffic? So in the morning, I was in the car, and I saw many policemen to control the traffic, right? But in the near future, right, we have a lot of autonomous car, okay? And how can we control this kind of traffic? And also, as a second example, I'm going to talk about the EEG data, which is the brain wave. When you think, from your brain, there is a data, the waves from your brain. So how can we collect the data from your brain, and how can we use this data? Okay, for example, we are focusing on detecting some medical disease, such as seizure. Okay, I'm not so sure how many of you are familiar with this kind of diseases, but in Korea we have a lot of patients for this disease. Okay, and finally, climate change. It's really important nowadays. So I want to explain my experience about climate change by using AI techniques or anomaly detection methods. Okay, and finally, I prepared several slides or 2 or 3 pages to talk about open issues. I know most of you are undergraduate students, but if you go to the a master PhD course, you will find out what is the open issue, right? And then you can do some research. So I want to share this kind of issues. This is open. A lot of people are still working on these problems. So the anomaly localization and early detection will be the open issue in my talk. Okay. Okay. So what is the multiple time series? Yesterday, I was talking about the anomaly detection from single time series, only one data streams, okay? Like room temperature over time, okay? So daytime, nighttime, And also the temperature during the year, like spring, summer, fall, winter. Yeah. We have the time series data, okay? But this is just a single source, okay? The temperature, this is only information you have. But in the real world, if you see the many different applications, you will have this kind of time series, like a multiple time series. Okay? So actually, in this room, we have many different environmental information, right? So for example, temperature, right? And also we can consider humidity, right? And also we can consider many different environment information, right? You know what I'm saying? So if you consider many different applications, you can consider this kind of problems. This is like a stock market. I'm not so sure how many of you are familiar with stock market, but in Korea, in USA, this kind of market is very critical. For example, Samsung Electronics, Hyundai Motors, we have many companies on stock market, and the price is dramatically, moving over time. So we want to understand why the price is changing over time, and also we want to understand the effects between the prices. Okay, so for example, the price for oil, okay, or the currency rates, okay, is changing, and this changes effects to the company's price. Okay, so it's very critical. It's really sensitive for the business. So people want to understand how the price is changing over time, right? So, for example, we have many different time series, and they are effects with each other. Something is going up, something going down, something going up, something going down, right? So it's really critical in business area. So we want to understand, and we want to understand where is the abnormal patterns from these multiple data streams, multiple time series. Okay, this is, I'm not so sure. I have several professors in economic departments or financial department. They are always talking about this data, right? So nowadays they are also focusing on deep learning to detect, to understand what kind of patterns, what kind of anomaly patterns in the data. So we have this kind of data, and how can we detect anomalies? And yesterday, one of the deep learning model is RNN, right? Recurrent neural network. So this is very strong with the data stream, such as time series, right? The temperature. You have a time series data, and you can apply RNN model, and you can easily understand how the data is changing over time, right? So, but in this case, the most important assumption was this data set is mutually independent, right? So we assume that all the data stream is changing without any effects from other data, okay? That was assumption yesterday, right? So we talk about, for example, LSTM as a most well-known example for RNN, right? You understand? So now today we are talking about multivariant, multiple data streams, and in real world, these data effects with each other, right? Strongly, sometimes weakly, sometimes strongly, right? So in real world, most of the data streams are coupled. So coupled means they are dependent with each other. Something going up, something going down. Okay? So for example, the the currency rate, for example, like US dollar and Vietnamese dong is changing, right? Sometimes going up, sometimes going down. And it affects to your price. For example, like if you buy something from other company or something from other countries, the currency rate affects the price for the price for another stuff, right? You know what I'm saying, right? So it's always changing. They are effect with each other. There is some kind of effect, cause and effects. Okay, so we need to consider the relationship between the data streams. This is what I'm talking about. Okay. The last one. So how can we detect anomalies from the multiple data streams? Okay, which are dependent with each other. If they are changing independently, there is no problem. We can just consider how can we apply RSTM or GRU for understanding the data stream. But the problem is they are dependent with each other. Okay? It's not easy. You know what I'm saying? So it's really, really complex problem. But most of the real case, most of the application in real world, you have to consider the dependencies between the data stream. Okay? Okay, so you have the multiple data stream, and you want to understand when and where there is abnormal patterns, right? So basic idea here, we are talking about dependency learning. Yesterday, you remember I was prepared several categories. Okay, so like the first category is to consider the mapping functions. Okay, so I'm going back to the example. You have 1, 2, 3, 4, 5 different data streams. How can we understand the dependencies between data stream? You have 5 different data streams. Where is the dependencies? Which data depends on which data? You understand my question? Okay. So it's not easy, right? So in this case, we have to consider the dependency learning among the data stream, right? So the temperature is going up, humidity is going down, right? Something like this. The price of oil is increasing, the currency rate is going down, right? So this is the dependency learning on our system, on our study. So the basic idea, very simple, but I was thinking this is really, really interesting idea. We want to represent our data stream as a dynamic graph over time. You have a graph, so I'm going to talk about more details on graph, but you have a graph, and your graph has a link, right? Link between the nodes, and these links are changing over time. Sometimes it's a very strong dependency, sometimes it's weak, sometimes strong, weak, weak, strong, something like this, okay? Your graph is changing over time. So you have this kind of multivariate time series, multiple data streams, and sometimes in the beginning there is no dependency, it's a very weak dependency, but over time you can find out there is a dependencies, right? So the question is, how can we understand the dependency between the data stream, okay? This is what I'm talking about now here. Okay. So, in order to represent your multiple data stream, and also you want to understand the dependency between the data stream, now we are talking about graph embedding. So, the last one, okay? Graph embedding. So, graph embedding can apply for this issue. This is what I proposed in my papers. I have several research papers, like several SCI journals. I'm not, well, professors want to publish the research on the journals, and I have several papers with graph embedding, and it has been successfully published, and I have many citations with graph embedding for anomaly detections. Anyway, I'm going to explain more details. Okay, let's back to here. Okay, I'm going to talk about graph embedding now. So you have a graph in real world, like I said before, right? So what is graph? What is graph? Anyone? So you guys already take the data structure, right? Data structure or algorithms and so on, right? So everybody knows what is graph. So graph is a general language for describing and modeling complex systems. It's a very general description. What is the graph, right? So the graph is composed of a set of nodes, right? You have a set of nodes, and there is a connection, the links between the nodes, which is called edges, right? There is a node and edge, and sometimes these nodes and edges can be labeled. Okay, so also we can call this as a type of nodes, okay, and attributes. So here we have yesterday we had 200 students, but today we just have 100 students, half I think. But anyway, if you consider the social networks, this is also some kind of graph, right? So we have social networks. And all of you, all of us, are some kind of nodes, right? And if you know each other, if you know with each other, it's some kind of edge between the nodes. And what could be the type? And also, you guys are affiliated with the PTIT, right? And we can put some PTIT as a node, and you are one of the students from PTIT, right? You know what I'm saying? So there is a node for the students. Also, there is a node for the university, right? So we have many different types of nodes in your graph, in your social networks. And also relationships. It's a very interesting. We have to consider what kind of relationship you have to consider, right? So between you and your friends, right? You know your friends, it's a nose, acquaintance. You know someone, right? But if you consider the relationship between you and PTIT, it's not friends, right? It's affiliation. You are the student of PTIT, right? So you have to consider the relationship between the nodes. And also you have to consider the strengths. You know what I'm saying? Strengths. So you know, you have, for example, you have 5 students, or 5 friends, or 3 friends. And some friends are very strong, right? You like these friends very, very, very much. It's very strong. But sometimes you don't like these friends, right? And this is a weak relationship. So you have to consider the strengths of the relationship. And finally, also we have to consider the structure. Okay? Once you have the graph, once you have the social network, you can consider the topologies, the structure of the graph, structure of social network. For example, some friends are, someone has a lot of friends, right? With a very strong relationship. So it means that he's very powerful. You know what I'm saying? He is in the center of your community. He has a very strong power. You know what I'm saying? So you have to, somehow you can find out who is more strong than others, who is more powerful than the other friends, right? So if you consider this kind of topologies, you can find out the centralities and also the betweenness, centralities, right? And also, in Google they are using the page rank for the websites, web pages, right? So somehow you can use this kind of idea to understand the structure of the graph. Okay, I'm talking about the graph, okay, in general, okay? In our world, we have many, examples on graph. So for example, internet, the computer networks, they are connected with each other, and you can represent this network as a graph. And also social network, I already explained about this, right? So social network, like a Twitter, Facebook, and also information retrieval system, they also represent it as a graph. And biomedical, chemical, they have some kind of RNA, DNA, right? So they are also represented as some kind of graph, okay? And okay, programming graph. So all of you are from computer science, am I right? So when you write some code, like a Python or C programming, you have to make some kind of functions, right? So these functions are called with each other, right? So function A called function B. You can have some kind of link between the functions. So this is the graph for the codes, right? The program. And most interesting, recently we are talking about scene graph in the image processing. Okay, so if you yesterday we talking about we have talked about CNN for image processing, right? Object recognition. So if you have some image, you have to understand the scene. What is the meaning of this image? Okay? So now if I take a photo of you, right? So I have several students and they are listening to me, and they try to understand what I'm saying, right? So this is the understanding of the image, the scene graph. So anyway, in the world, in our world, in real world, we have many different graphs, and somehow we want to understand this graph, right? Because there are a lot of useful information, useful patterns. And the question is, the size of graph is really, really huge, right? Even here, we have 100 students. If you consider how to build a graph, it's really, really complex, right? So the people want to apply some AI techniques to understand your graph, right? More efficiently, and so on, right? So recently we have a lot of papers from AI communities. If you Google graph embedding or graph neural network, you will have a lot of papers, right? And the first paper about graph embedding was published on 2009 in the Triple AI, right? One of the best conference in AI. So a lot of people are talking about graph embedding, graph neural networks, and so on, right? So today, now I'm starting to talk about the graph embedding, okay? So what is graph embedding? Anyone who is familiar with the word embedding? Do you have a lot of words? Yeah. There's anyone else? No. Okay. There is a lot of words. You want to find out the relationship between the words. You know the man minus woman is queen plus king, something like that. Do you know about this? No? Okay. So if you Google words embedding, you will find out many interesting examples, and you can easily understand what I'm talking. But now, instead of words, instead of text, we are talking about graph. Okay? You have a graph. How can we embed? Okay? So, like I said here, we have a social network, which is the graph, right? So you have the. I got this image from Google, but you can say we have a social network, which is the graph, right? And we can represent our social network into the two-dimensional matrix, right? I know someone, he knows someone else, You know what I'm saying? So if they know, you can put 1. If there's no relationship between the people, you can put 0, right? So you have this kind of adjacency matrix, 2-dimensional matrix, okay? So you can use this kind of matrix to understand the social network, right? But there is a limitation. The first limitation is, like I said, we have a lot of nodes, a lot of people, right? For example, in Facebook and Twitter, can you guess how many users they have? Facebook, how many users they have in Facebook? Yeah, more than billion, right? So if you consider sorry? Yeah. Thank you for your answer. I can say huge, right? We cannot imagine how many users they have, right? So it's extremely high dimension. If you consider the 2-dimensional matrix, okay, you have like a 1 billion by 1 billion matrix. It's not possible to process, right? So it's really, really huge. And there is no global structure information integrated, right? So we have local information in the graph, right? And how can we integrate this local information, right? It's really, really hard. And permutation variance, right? So you have to consider the many different combinations, right? So it's really, really difficult. So somehow we can have some kind of representation with a vector, feature vectors. So I got it from some bioinformatics paper. Like if you consider the nodes with the DNA or RNA or some sequence of the DNA, you can represent this kind of information with a lot of different types of graph. Okay. Maybe you can think about this graph as like a components, basic components, okay? So you have, for example, you have this kind of structure, okay, graph, and you want to understand what is the components, what is the basic components of this. On the right hand side, there is a certain graph you want to understand, right? And then you can use the basic components, okay? How can we organize this graph by using the basic components, okay? You understand? So this is a very, very basic ideas, right? And so people are thinking about how can we improve. How can we find a better solution? Okay? So once you have graph, very well-known network, Karade network, this is a very well-known example in social networks. If you have this kind of graph, somehow you can put the nodes in the feature space. You remember yesterday I was talking about the mapping function. Mapping function, like in case of support vector machine, there is a kernel function, and your original data seems very complex. It's not easy to classify, but once you apply the kernel functions, you can have another, another feature space, right? And you can easily separate your data. But anyway, in this case, you have a graph as the original data, okay? Karade networks, and if you can put all the nodes in a certain embedding space, a feature space, somehow we can separate, right? Somehow we can separate once you have the graph, it's not easy to understand, right? You know what I'm saying? I put some color, but if you have no color, if you have no information, if you just have okay, for example, we know 100 students with the social network. How can we separate? It's not possible, right? It's not easy. It's very difficult. But if you consider the embedding, if you consider some mathematical function to transform your information into here, okay? Somehow we can easily classify your information, your data, right? You know what I'm saying? So now we are going to talk about how to embed, how to transform from the graph to the embedding space, okay? So the first idea is the shallow network embedding. So it's also very simple ideas. So inspired by the word embedding. Maybe I didn't put the word embedding slide, but like I said before, 10 minutes ago, like a man and woman, the relationship between man and woman will be very similar with the relationship between king and queen, right? For example, you have Hanoi is the capital city of Vietnam, right? So Hanoi and Vietnam is very similar with the Seoul and Korea. You know what I'm saying? So if you have a lot of data, you can find out this kind of relationship from your data, from your texts, okay? And they have some kind of idea to embed the words like skipgram or CBAL, continuous bag of words, something like this kind of algorithm can be applied for word embedding. But it's also very similar with the graph embedding. So now we are talking about graph, okay? Not words. But idea is very similar. So here So now we are talking about graph embedding, and graph is composed of a set of words. Set of nodes and edges. Okay, so node can be embedded, determined by the context. Okay, so in this case, there are several well-known methods, such as deep work. You know the random process. You have the graph, and by using some random process, you can move to the graph, right? So here is the idea for deep work. Okay, so in this case, deep work has been published in KDD 2014, right? Like almost 10 years ago, and also very well-known example here, line or node to back. Okay, so this kind of algorithm can embed your nodes in the graph into the embedding space, and you can find out the relationship between nodes more easily. So here is an example. So we can consider the first of the proximity. The proximity you can consider as the number of edges between two nodes. Okay. So here we have two types of. I put different color here, blue and orange. Okay. So the basic assumption is two nodes are similar if they are connected, right? If they connected, we know that they are very similar. Okay, this is the assumption. So here we can use this kind of mathematical formulation to find out the value. Okay. So here we have a graph, and here we have a graph, and two orange nodes are connected with each other. So we assume that they are very similar. Okay. So limitation, the links are very sparse. Sparse means it's not dense. Okay, there is only few connections between the nodes. So it's not efficient. It's not sufficient. It's not sufficient to embed. And we also want to consider the objective function because we want to have some kind of goal. Okay, you want to consider minimize the KR divergence between between the link distribution, right? So we can use this kind of function to minimize the error, minimize the divergences, okay? Yeah. So this is also very well-known objective function, KL divergency, right? So if you open the AI book and machine learning, you can easily find out this. Okay, so not only the first order proximity, please remind, I want to remind, the proximity means a connection, okay? Connection. You see? So if I know there is someone who knows everyone. If you, some of you are known everyone, right? He has a very powerful, right? Powerful position. He has a very powerful position. Okay? So he has a very powerful first order proximity, right? But now I'm talking about second order proximity. Okay? So second order proximity is we can allow two connections. Okay? So here the orange one has two connections, right? So we can consider the more general cases, okay? To understand the node impact. So in this case, we are using some conditional probability to measure the second order proximity. So in this case, we are using like a P2, which is the second order proximity. So given Vi, what is the probability of Vj? So we can use this kind of mathematical formulation to measure the second order proximity. It looks a little bit complex, but please understand the basic concept, okay? And again, we also want to use some objective function to find out, you know, to minimize the divergences. Okay, so also the same. We can use the KL divergences to minimize. Okay, as an objective function. So here is an example for the equations. Okay, so also people are talking about many different cases. So negative sampling and for the optimizations, right? So you have many different links, connections between the nodes in your graph, and then you can consider this kind of idea for like optimization, okay, of the node embedding. Okay, so what? Okay, maybe there is some examples for your understanding, but now we are talking about graph, which is the knowledge. Okay. So, like I said, in our world, we have many different kinds of graph. So not only the social network, not only the biological, graph. Okay. Now we are talking about knowledge graph. So you have a knowledge, and you can represent your knowledge with a graph. Okay. So here is an example. Mona Lisa. Mona Lisa is like a famous paints in Louvre in Paris, right? So you can represent. Okay, Mona Lisa is created by the Leonardo da Vinci, and is in the Louvre Museum in Paris, and the Louvre is located in Paris, and Paris is a kind of city, and Eiffel Tower is located in Paris, something like this. Okay, and Google, ChatGPT, or what else? A lot of AI systems are using this kind of information somehow, right? And Wikipedia also, they have this kind of information. So anyway, I'm talking about the graph embedding now, but this graph represents human knowledge, right? You have a human knowledge, and like I said, it's a very complex, right? It's a very, very huge. Like if you consider the human knowledge, it's really, complex, right? As you see here. And somehow we want to understand, right? We want to understand the relationship between the nodes, the relationship between the edges, and so on, right? So that's why we are talking about knowledge graph embedding, right? So this is knowledge graph, and they have multiple relational graph data. Also, this is called heterogeneous information network. You know what is heterogeneous is? Okay, heterogeneous. So in this case, you have many different types of nodes and many different types of edges, right? So in this case, we call this is information network, which is heterogeneous, right? So once you have this kind of network, we want to understand. So they provide a structural representation of semantic relationships between the real world entities. Okay? So if you Google like Hanoi, Vietnam, and then you will find out a lot of websites, and also you will have some link for the Wikipedia, right? Wikipedia. If you go to the Wikipedia, you will find out info box. You know, info box. There is some box on the right-hand side. You will see what is the population of Hanoi and the history. What else? Some important information on the right-hand side, and you will have knowledge graph. Okay, inside the Wikipedia. Right? So this is called DBpedia. Right? I'm not going to more details, but if you are interested in this kind of knowledge, you will have it on the website. Okay. So anyway, here you have the knowledge graph about Mona Lisa and Louvre and Paris. So you will have this kind of information, HRT. So here H means head, and R means relationship, and T means a tail. Okay, so here this is an example. Eiffel Tower is located in Paris. Okay, so Eiffel Tower is head, and tail is Paris, and is located in is a relationship between two entities. And also this is called subject, predicates, objects, right? So I don't want to go details, but if you are interested in knowledge graph, you can find out more details here. Okay. So like I said, knowledge graph is everywhere. I gave you several examples like a ChatGPT and Google, but here if you see many different general search engines, like in China, Baidu, Freebase also very famous, and Yahoo is another famous knowledge graph, and bio and medical knowledge graph, and product graph and e-commerce, they also have some knowledge graph because they need to understand the meaning between the products, and common sense knowledge graph and natural language processing. Okay, so human knowledge like taxonomical, biological, and commercial and linguistic knowledge can be represented as a knowledge graph. And most importantly, this information, this knowledge graph, somehow opened. Like for example, the Yahoo, Freebase, Wikipedia is already open, so you can download it. Okay, you can use whenever you want. as a professor in university, I'm always asking my student to download it, and you can, ask. I'm always ask them to use this kind of open data for the projects. Okay, so it's really important. So I want to give you some motivation. If you have any chance, please try to use this kind of knowledge graph. Okay, so biology, products, and common sense. So WordNet, I'm not so sure in Vietnamese language you have the WordNet, but okay, anyway, I don't want to spend more time, but there are knowledge graph in many different domains. You can download it, and they are represented as a graph. Okay, this is what I'm trying to explain. So, like I said, there are many applications with the knowledge graph. Okay, so most recently, ChatGPT has a lot of impacts. So they are using knowledge graph for natural language processing. So not only the deep learning, but also they have this kind of knowledge for interaction with a human. Okay, and eBay, Netflix, Amazon, they have a recommendation system. They want to recommend some kind of items, some kind of products to the people, and they're always using the knowledge graph. Okay, so I'm going to skip. So in Google, you can ask me, okay, professor, where is the knowledge graph in Google, right? So if you search something on Google, like Bloomberg, who is the most famous guy in financial area, and you will have the information like this. Okay, so on the right hand side, you have the facts from knowledge graph. Okay, so not only the Wikipedia, but also Google has this kind of knowledge. So the parties, the birthday, heights, and so on, right? And the eBay or Netflix, they also have the knowledge graph for the recommendations. And this is a very well-known system for the recommendations. So I'm sorry, I don't have a laser here, but if you see the knowledge graph they have, all the information is can be used for the recommendations. Okay, so there is a Michelle Obama, Barack Obama, and they have this kind of information for generating the recommendations. Okay, so when you search some book, when you search some products, when you search some music, and somehow the system can understand what is the context of the people, right? So I'm trying to explain the knowledge graph, okay? So because in case of knowledge graph, the graph embedding also very important, right? Can you guess what is the size of the knowledge graph in eBay or Netflix? It's really huge, right? That's what I'm talking about here. Okay, so knowledge graph for the recommendations, and also biology, like in medical science or in biology, chemistry, they have this kind of informations, and they want to represent this information for knowledge graph. Okay, so they can have this kind of knowledge graph. For example, protein interaction. Okay, for example, they want to discover some drugs. Like when you have some disease, you want to find out what protein has effects with a certain disease. So you can use this kind of information to design new drug. Okay? So they're using this knowledge graph, like a transfer models, and also they are using some knowledge model for this. Okay? So I have shown several examples, okay? There is a knowledge graph, and this knowledge graph can be used for many different domains, many different applications. And what is the goal, right? Why I'm talking about knowledge graph with the anomaly detection? So please remember, I'm talking about graph embedding, and I am trying to explain what is graph embedding with the knowledge graph. Okay, I'm just talking so many times with the graph, right? So anyway, the goal is the encode means mapping, okay? Mapping the nodes in the graph to the embedding space. So encode entities as low-dimensional vectors and relations as a parametric algebraic operations. This seems very strange, but most important information is you have the knowledge as a graph, okay? You want to put all the nodes in your knowledge into embedding space, okay? This is the goal. And then you will find out the relationship between the entities, okay? So input is relational facts, okay? So for example, Hanoi is a capital city of Vietnam, okay? So Hanoi, capital, Vietnam. This is the information, this is input as a knowledge, okay? And output is a relationship of the object and relations. So once you embed your knowledge into embedding space, okay, so for example, Hanoi is the capital of Vietnam, Seoul is the capital of Korea, and Paris is the capital of France, okay? So these capital cities, Hanoi, Seoul, Paris, will locate it very similar, very closely, right? And the country, France, Vietnam, Korea, will be placed with a small distance, right? This is what we are trying to do. So, for example, this is an example like UCLA, the university in LA, right? California, right? So UCLA is located in Los Angeles, and there is a score function. Okay, you want to encode, you want to map all the nodes, right, in the embedding space. So you have to define some kind of score function. Okay. For example, this is F, R, H, and T. So what is H and T? Remember the input is a relation facts, okay? For example, Hanoi is a capital city of Vietnam. So in this case, H is Hanoi and T is Vietnam, okay? So you have to consider some kind of scoring function to transform, to encode your nodes, okay? And define also loss function to guide the training. So you will have a lot of data set, right? In your knowledge graph, okay? Korea is the capital of Seoul is the capital of Korea, Hanoi is the capital of Vietnam, Paris is the capital of France, right? This is the training data set, right? And you will have this data as an input, and you repeat the scoring function, right? And finally, you have to consider the loss function to minimize, okay? This is basically the idea for knowledge graph embedding, okay? Again, it has a long history, like 10 years, more than 10 years. And there are many ideas to map your knowledge graph into the embedding space, okay? So here I put several algorithms, right? So SE, trans-E. So here, if you see the trans-E, trans-X, and also the last one, I don't know how to pronounce, convolution embedding. They are very, very famous, and if you Google, you can download open sources. So it's easy to implement your system for knowledge graph embedding. So they have this kind of scoring functions, okay? And then you can easily embed your knowledge graph. It doesn't matter what is your size of, what is the size of your knowledge graph. Even you have a really huge knowledge graph, you can easily embed. Okay, so this is the very simple idea for scoring function, which is called trans-E. Like I said, this is one of the famous, world famous algorithms for the knowledge graph embedding. So here, so you have an H, which is head, and T, which is a tail, and there is an R, right? So this is the idea for embedding, right? Okay, this is an example, right? This is an example for the node embedding, right? So you have China, USA, UK, and then there is capital cities like Beijing, Washington DC, right? DC and London. And you will see here the countries are on how can I say, left and bottom, right? And you will see the location of the capital cities. It's right up, right? So we easily understand that they are in the similar places, right? You understand what I'm saying? It's really, by embedding your knowledge graph, we can easily understand what is the meaning. Maybe it's not, okay, maybe, I really want to give you more motivations, understandings. Here, if you consider the knowledge graph, it looks very simple, right? Easy to understand. Am I right? But if you consider really huge, it's not easy to understand, right? It's really hard to understand. So that's why we have to consider the embedding. How can we help people to understand more efficiently? This is what I'm talking, right? Knowledge graph embedding. Okay, so like I said, trans-E is the very famous algorithms, and this is the scoring function, okay? And there is an objective function to minimize the loss, okay? So in this case, margin-based ranking loss has been used to measuring the loss of the embedding, okay? Okay. Of course, this is a very well-known and also very efficient algorithms for graph embedding and knowledge graph embeddings, but there is some kind of limitations. So, for example, the trans-E only focusing on one-to-one mappings, okay? Like Vietnam and Hanoi. So Hanoi is the capital city of the Vietnam. This is one-to-one mapping, right? But Hanoi has a many different relationships, right? So, what is the next city of Hanoi? Okay, Haiphong. Haiphong is very close to Hanoi, right? So, so Haiphong is close to Hanoi, for example, and it's not easy to embed this kind of multiple mappings, right? So, we have to extend the ideas for multiple mappings, and also symmetrics. So symmetric means, what is the symmetric? Symmetry. So if A and B, B will A, right? It's a symmetric, right? But this is anti-symmetric. So if there is a relationship between H and T, the relationship between T and H is not true. Okay? But in real world, sometimes it's okay, but sometimes it's not okay, right? So it depends on the domain, it depends on the situation. We have to fix it. We have to fix the problem, okay? So we cannot model the symmetric relationship, right? So this is the problem of the trans E. And also anti-reflexive. So for example, RHH is not the truth. So cannot model reflexive relationship. Synonyms. So synonym is the words who have the same meaning, right? So in this case, the trans E cannot represent. Okay? Okay, there is more, but okay, let me. Okay, can we have what time is it now? We start at 9:15, 20, and what time is it now? Sorry? 10:30. Can we have a 5 minutes break and we will start again at King? I have only like 20 students in a very small room. I was expecting some blackboard and writing some, doing some exercise together. But when I arrived here, I was really surprised because 200 students, very big room. It's just like a conference. Most of you are undergraduate students, third year, second year, and it could be better if I prepare some slides with a lot of images, a lot of examples, some applications. It could be more interesting. But I'm sorry about that. Maybe if I have another chance, I will do it more in the easy way. But anyway, I want to give you some motivation. Okay? So anomaly detection, deep learning, AI is important, and people are considering how to solve the problem. Okay? So let's back to the talk I gave you for the moments. Knowledge graph is really, really important. I don't know how to emphasize about this, but it's really important, especially in AI, because even you have a very, very good natural language processing. If you don't have any knowledge, what happened? They don't know how to answer, right? So you have to consider how to represent your knowledge and how can you process to answer the question from the users, right? Okay. That's why I'm talking about knowledge graph embedding, and there are many different items. I'm going to skip it. Okay, I'm going to skip it several slides to have more, useful insight for you. Like I said, there are so many different algorithms, okay, to embed, to process the knowledge graph. The trans E, you have to consider multiple relationship between the entities in your knowledge graph. And rotate E, this is also very interesting because sometimes you have a knowledge and you want to represent this knowledge in a sphere space, like a circle, right? Not a Euclidean distance, Euclidean space, X and Y. Okay? So they propose this kind of idea for, also called rotate E, something like this. They consider the angles, right? And this is some objective functions. I'm going to skip it. Okay? So pros and cons, what is advantage and what is disadvantage. You can download a file from my website. Okay? You can access my website, you can download. Okay. Then the last one is graph neural networks. So please remember that yesterday and so far we talked about neural networks or some machine learning methods. All the data is like labeled with what is it? What are you wearing? What happened? No, I'm just kidding. It's a special day, right? I know there is a kind of holiday. It's not a holiday, but there is something, right? This week? This weekend. Anyway. So I'm talking about the graph neural network. So usually we have a neural network and the data, the training data is like, for example, image file and the label. Okay, like a cat and dog, cat and dog, cat and dog. You know, you can use this kind of labels to train of your neural network, right? But here we are talking about graph neural network. It's a little bit different, right? Your data, your training data is graph. You know what I'm saying? You have a graph and you want to train your neural network with this graph data. So in this case, so I'm going to skip. So in this case, you have a graph, V and E, the set of nodes, which is here we call vertex, the same thing, right? The node and vertex, the same, right? And V and E, the E is edge between the nodes, okay? And you can represent V and E with a two-dimensional matrix, adjacency matrix. And here is X is a feature matrix of all the nodes. And we know that NV, okay, is a set of neighbors of the node V, okay? And you know the representation vector, embedding vector of the V, okay, node V at layer L, right? So please remember that we have a Faraday networks, and these nodes are embedded in a embedding space, right? So you can use this information when you train your neural network, right? So this is H, okay? Embedding score, embedding value, okay? So finally we will have a HL, which is the representation matrix. So you have the n by n matrix, for example, n by n matrix, and all the value is a result of the embedding. Okay? You can apply the trans E, you can apply the rotate E, you can apply many different embedding function, okay? And then you will have the H, okay? So you can use this information to train your neural network, okay? So in this case, you can have many extensions, like for example, aggregations, transformation, and also the combinations, right? For the graph. I'm talking about graph neural network, right? You have a graph, you want to use this graph as a training, okay? So this is an example, okay? So I want to compare with the CNN, okay? You remember what is CNN? You have the image file, for example, and you can represent the image file into two-dimensional matrix, like a convolution, like a feature extractions and transformation and so on, right? So you have an image, you can have the convolution, like a 4, right? It's not easy to explain without any lasers. But anyway, here you have the image file, and you will have the matrix, okay? And you have a convolution like this, okay? If you have a question, just ask me, okay? And different from CNN, we want to use a GNN, graph neural network, like this. You have the graph as an input, like A, B, C, D, E, F. And then you have the embedding space, right? All the nodes are measured with the score function, right? So, like for example, A has some value, B has some value, okay? So you can use this value when you have the training, okay? So, sorry? Yep. Yep, exactly. So there are also many ideas how to integrate CNN or RNN with the graph neural network, right? So here, the basic idea has been published in 2017. They call this is graph convolution network. Okay, so they try to apply the CNN concept from CNN for training the graph data. Okay. So it looks a little bit complex, but please understand the basic concept, okay? The idea of the GCN, the graph convolutional network. So the question is, sorry? Yep. This is different. Yeah. Thank you. So now I want to talk about the question about the parameters. So you have a lot of hyperparameters, right? So in GCN, how many parameters we have, right? So we have to assume that we need to assume that the initial number of features can be represented as with D0 dimension. We are starting from D0, right? And sometimes we have a lot of parameters. We have to train. We have to find the optimal, the values for the parameters, right? So we are starting from D0, but later we will have a D dimensions, right? So it will be extremely increased, right? So for this, of course, people are very smart. Every time we have new ideas. So this is a kind of extended ideas, okay? So the people say graph sage, okay? So they try to aggregate the parts of the graph. You can say this is subgraph, okay? With a subset of the parameters. And with these ideas, we can consider the mean, RSTM, and pooling, right? Okay, I'm going to skip about this. Also, we can consider attention model, right? So, okay, graph attention model. It's not actually. This is also called GAN, G-A-N, but please don't confuse with the generative adversary network, GAN model, generative models. It's not same as it, right? So it's completely different graph attention model. Okay, so this is how it works. Always it's important to consider the attention, right? So if you have a very long sentence, for example, you have to find out which word, which part of the sentence is more important than the other words, right? So in the graph, also the same. You have a very complex graph. You need to find out which part of the graph is more important than the others. So this is how it works. So they need to consider the attention, okay, for the graph. Okay, I saw several very complex equations and several ideas and so on, but most important thing is to consider the nodes and edges. The main goal is to understand the very complex graph, okay? So if you consider the node level, you can consider some similarity search. Okay, you have a graph, and you have a capital and country, capital, country, capital, country. Okay, and you want to know that what is the capital city of, for example, Cambodia. Okay, even there is no even there is no link. So I'm going to talk about link prediction. Okay? Your knowledge graph is not complete. You are missing. There is some missing knowledge. Once you embed your knowledge, you can find out what is the capital city of Cambodia. Even there is no knowledge. You know what I'm saying? This is a link prediction and a similarity search. And also we can have some classification, right? So like a classification of cities, classification of the countries, something like this. And community detection, like we have a social network among the people in this room, and we can identify how can we make communities, okay? So by using the embedding, okay? By using the graph embedding. And also ranking is possible. So if you have the very powerful position, you will have the first rank, okay? So by using some kind of scoring functions, you can find out who is most powerful person in the graph, in the social network, for example, right? This is the what we have to do, what we want to do with the graph. This one is the node level, and if you consider the graph level, okay? Graph level means okay, for example, the student in this room, we can make a social network, right? But what about the other student in other rooms? Okay, we have a social network here, like 100 students, we can make a social network, right? What about the other room? There is another student, there is another graph, right? You know what I'm saying? If you have many different graphs, you want to understand the relationship between the graph. Okay, in this case also we can consider the similarity search, right? Which graphs are similar? I'm not so sure, I'm not an expert in social science, but maybe some human behaviors are very similar with Korea, Vietnam, very similar, but some behaviors are not similar, right? Completely different. I don't have a good example. I'm just trying to explain what is the graph level, because we have many different graphs. Social network from Vietnam, or social network from PTIT, social network from Chungang University in Korea. Somehow we can find out the similarity or distance between the social network, right? This is the graph level embedding. We embed the graphs, and somehow we can find out the relationship between the graphs. And frequent pattern mining, and also if there is many graphs, we want to find out isomorphism, right? Isomorphism is whether the structure is similar or not, right? You see? And graph mapping, also very important. Classification, clustering, and graph generations. I really want to emphasize this part because my research, the next part of my talk, it will be about the graph level embedding, okay? Okay, so I'm going to quick. It's a little bit difficult. So you remember yesterday I was talking about semi-supervised learning because the labeling the data, labeling the training data set is very expensive. It takes a lot of time. You need to ask people to label, right? It takes time. It's very expensive. So we don't have enough number of training data set in the real world. Only few of data has been labeled, right? Like a 10%, 20%. So how can we solve this problem? So we are using semi-supervised learning to estimation. We can use some estimation to increase the number of the training data set. So I'm going to skip. So it will be the same. It will be the same with the graph data. So here there is some example. Social network. I gave you so many times about social network. The social network between the people in this room. We can use these ideas, these methods, to identify the social network, the accounts is bot or not. It's also very important in Korea because some politicians make some fake ID, fake bot, to make a lot of news, a lot of replies, and so on, right? So it's really, really important nowadays, especially in Korea. And we can use this kind of AI techniques to identify this is a bot, this is a real human, okay? Yeah, exactly. Deep fake. Okay, deep fake, they are using some GAN model, the generative adversarial network model, to generate fake image, fake movie, fake video, right? But in this case, we want to identify a certain node is a bot. A little bit different. Yeah, a little bit different. Because it's a very critical in politics, right? Like a fake ID, you can generate like 1 million fake ID, and then you have some kind of message, and it affects to your society, right? It's very important nowadays. Another example is citation network. So citation network is also very important nowadays because when you evaluate your professors, you're writing papers, okay? You're writing papers. How can you decide your paper is good or not? You can consider, you can count how often, how many times the paper has been cited, right? You know what I'm saying? Yeah. Number of citations, and you can say, oh, maybe this paper is really good, right? This is very simple idea. So, from the citation, we can make like a citation network between the paper, okay? So this is a graph, another example for the graph. The other one is a program graph that I already explained in this morning, right? So you writing some code, there is a list of functions, and the function calling to another function, right? So you can make some kind of graph among the codes, right? In this case, also you can consider variables in the function. If you writing code, there is a variables declared in the function, right? And then you can make some kind of graph. And then you can decide which variable is very important in your code, right? So this is how it works. And link prediction is really, really important. I also really want to emphasize this is really important. Like I said, your knowledge graph is not complete, it's not perfect. There is some mistake. You are missing some links between the nodes, right? You have a list of the capital city, you have a list of country, but sometimes you are missing the links, right? But even there are some missing links, you can predict, okay? If you have like again, I'm explaining again. The Vietnam, Korea, France, Hanoi, Seoul, Paris, you made a mistake. Oh, you didn't put the link between France and Paris. But once you embed your knowledge graph, you can predict, oh, France and Paris, this is capital. Okay? You know what I'm saying? So here is an idea of how to predict a link. So you remember the encoding, right? Yesterday I was talking about autoencoder as an example. Encoding and decoding, you can reconstruct your original data with a very small errors, right? Where is the example? Okay, you remember the Mona Lisa, right? Mona Lisa, Paris, Louvre, right? And then you can embed first, right? Once you embed, your all the nodes in your graph has been embedded in a space, feature space. And then you can find out the relationship between the nodes, even there's no links, right? Because some nodes are very placed in a very small distance, right? So you can use these kind of functions to predict. So here is an example again. So social networks, okay. Most of you knows the LinkedIn, right? LinkedIn, Facebook, right? Sometimes when you log in your system, you have some recommendation. You may know someone, right? Everybody knows LinkedIn, right? Okay. So how LinkedIn provide this kind of recommendation? How can? So they provide this kind of recommendation with the embedding, graph embedding. Very simple example. They know your affiliation, right? You are the student in PTIT, right? By using the affiliation, you can embed your information to the space, right? And then you can find out, oh, they are in the same university, but there is no link, and then they can generate a recommendation. You know what I'm saying? Very simple example, right? Citation networks, also the same. So you have the citation between the papers, right? Do you know the ResearchGate? One of the well-known service for the academic area. If you log in the service, or you will have a lot of emails, oh, please read this paper. This paper seems very useful for your research, something like that, okay? So they are using embedding of the citation network, and then they can generate a recommendation. Medical networks and program-driven graph, also the same, right? I'm going to skip. Okay, graph classification. This is about the graph level embedding, okay? So not node level, okay? So you have several different graphs, graph 1, 2, 3, 4, 5, okay? You want to classify the graph itself, okay? Graph 1, graph 2, very similar, you want to cluster. There is another cluster for the graphs, right? So you can use, again, mathematically, you can use the same functions, encoding and decoding, right? Once you decode, you can find out the loss functions, and you can decide, oh, there is a cluster for the graphs. Okay, this is an example. I already mentioned several times. The chemistry, biology is really important because I'm not so sure in Vietnam. I'm sorry, I always compare with Korea because I have a lot of experience with the Korean people. When people want to discover the drugs, how can they do it? They need to produce some new chemical. How can they do it? What is the idea? Anyone from chemistry? No. How can they do it? There is many different chemical components. They need to try, right? they need to try, oh, component A, chemical 1, chemical 2, they need to mix together, right? They try to make a new components. But what do you think? This is very expensive. It takes a lot of time, right? In the lab, in the laboratory, they mix A and B, and they test, oh, whether it's good or not. They need to test. It takes a lot of time, right? But if you know if you know the meaning of the chemical, or if you know the meaning of the biological structure, you can simulate. You don't need to try, right? You don't need to mix together, right? But you can do it on simulation first. You test with the simulation first in your computer, and the chance, the probability of success is higher than something, like 80%, 90%. And then you decide test in the real lab, okay? This is how it works nowadays. People never try, without any reason, okay? So this is how it works with the AI, for the chemistry, for the biologist, for the physicist, something like that, okay? It's really, really important because always it's a matter of money, right? It's a matter of money. You have to spend a lot of money to make a new products, new drugs, okay? So if you have simulation, then you can save your money, right? It's very, good for your financial issue, right? So chemical, protein, and program-driven graphs, and so on. Okay, anyway, if you want to cluster your graphs, you have to measure some distance or similarity between the graph. Graph 1, graph 2, you need to measure the similarity or distance, right? So in this case, you can use this kind of functions. Okay, so this is also very well-known example. Published in 2019, a few years ago, in AAAI. So they are using this kind of how can I say, some procedures. Okay, once you have a graph, how can you find out the similarity between the graph? Okay, this is what this paper proposed in the paper. Okay, and like I said, in chemistry or biology, they want to discover the drugs for the disease. So in this case, they are using this kind of architecture to find out the similarity between the graphs. And program database. You can write some Python code or C code, right? Am I right? Java, C, Python, and And ChatGPT is really powerful, right? When you ask ChatGPT, please write some code for this, and they will give you the code. And yeah.
You know, Java programming language, when we do like object-oriented programming, and now AEC assembly as well. Both of them. I've started using it for both of them, and it feels really powerful.
I'm talking about the writing codes, like programming, like he said, Java, any programming languages. Somehow we can use some AI. You can save your time, right? You can ask AI, please write my code, and you can use the result from AI for developing your softwares, right? So this is some kind of new trends. I'm not so sure in Vietnam, but in Korea we are always using ChatGPT or AI when we teach as a professor, okay? As a teacher, I'm always asking my students to please use AI, when they need to write some code. But anyway, so when you write some code, you will have several different codes, right? Like a sorting or searching, you will have many different codes. And can you guess the similarity between the codes? What do you think? You need to write some code for quick sort. Okay, you need to write some code for quick sort, and you ask ChatGPT, okay, please give me some code. And also you can ask Bard, Google AI, to write some code. Okay, and you have different results, but you need to decide which code will be used, right, for your project. So in this case, you have to consider the similarity between the codes. How can we do it? Okay, this is what I'm talking here. Code recommendation. Okay, there is some example. I put some slide because I was expecting 20 students, but we have a lot of students. So somehow you can access some links. This link to see how graph neural network is working. Okay. Summary. Very basic idea, basic concept for the graph embedding. We have a lot of different kinds of graph in our life, in our world. And since it's a very complex, you need to have some kind of embedding, encoding, okay? To have better understanding in a very short time, right? Easily. So I was explaining several ideas of graph embedding, and nowadays people propose a very different ideas, various ideas, smart ideas. So I was talking about line to back, node to back, and so on. And one of the important graph is knowledge graph. Human knowledge can be represented as a graph. So in this case, we can use several ideas like transit, OTT, to understand, to process your knowledge graph. And finally, we have seen graph neural network. How can we use the result from graph embedding to learn graphical information for your neural network? Okay, this is a reference. Okay, can you open the next slides? 4-1. Okay, so now it's about my research. Yes, thank you very much. So this topic is about my student and myself. And the paper has been published Information Fusion, one of the top journals. I'm very proud of this paper. Okay, and the second reference is Gun Lee, who is my PhD student. He's now working in the Chongqing University in China. This is from the PhD study. Okay, so I'm going to explain about deep learning and graph embedding for the anomaly detection with multiple time series. Okay, so this is the outline. Again, the background is we have the time series over time. Every day, every moment, we have a data, and this data is always changing. How can we understand this data, especially for anomaly detection? Okay, so yesterday I was talking about fire alarm, right? In this room, if there is a fire, we need to know as soon as possible, as earlier as possible, right? So this is the problem. This is the motivation of this study. So the sensors, we can measure some temperatures. There are also many different types of sensors, not only the temperature, but humidity, right? So we can monitor some work process in the factory, and also we can monitor our health, right? And infrastructures and so on. Okay, this is a very important slide. Please remember, right? Whenever I explain this idea, I have a question. How can we use anomaly detection? What is your goal? What is your next goal? Why do we have to consider anomaly detection? Maybe I should have explained yesterday, but now I'm asking to consider what is the next level, next step for the anomaly detection. You detect anomaly, and how can we use it? What do you think? The first goal is to pre-process your data, right? Like if you have a data stream, a lot of data, but sometimes you have a very strange data, right? And then you can remove it because you need to clean your data, right? You understand?
But what if it means something?
Sorry?
What if it means something?
Because maybe when you collect the data, maybe you made some mistake, right? You have a data, but the data is very noisy, right? A lot of noise. When you train your data, maybe there is some kind of mistake, right? So in this case, you have removed. This is called pre-processing, data cleaning, okay? But second goal, the next one, is understand the events, social events, okay? So like I said, fire, if there is an event, we have to know that there is a fire, there is a car accident, there is a financial problem, there is some events, right? So we can use these events to learn again. You know what I'm saying? Because please remember that anomalies are not, how can I say, it's very sparse, right? You know, there is a car accident, for example, and do you know that this is some kind of training? Before we train this kind of accident, we cannot guarantee, right? Okay. What is the good example? We cannot expect your anomalies, right? So in your training data set, you have no information about these anomalies, right? So you have a new events for the anomalies. How can you do it? You just remove it? No. You have to train again. Once you have a new anomalies, you have to train again and again, right? Yeah, retrain. Yeah. You have to train again and again, and then you can have better performance for the anomaly detection. This is what I'm talking, right? We have two different goals. Sorry?
But do we have to train the whole data set?
Yeah. Sometimes, you know, I was thinking this is very good. If I have a new experience, there is a bias, right? But sometimes it's conflict with my past experience. And then we have to fix it, right? So we need to compare with my past experience again and again. It's a really important issue in our case, because I want to, in this study, we want to propose a very, it's not very, but like a general framework, how to detect the anomalies and how to retrain, right? For the better detection. Okay, so like I said, as a first goal, if you have a data string, if there is an anomalies, you have to remove the noise. In this case, noise is anomalies. You have to remove it. Okay? Okay, second case, events of the interest. Fire alarm. Please remember the fire alarm, okay? So you have the data stream. So the blue one is a normal case, normal states. But in this case, the red case is abnormal, right? So if you have a very strange data coming, and you have to say, oh, we have a new event, right? Okay, this is also very interesting part. This is our idea. I'm very proud of these categories. In multiple data streams, we have, for example, we have 3 different data sources, data streams, and we can say there are 3 types of anomalies. Okay, the first one is points, the time points. When the fire happened, right? So this is the time points. And second is subsequence, the time interval, from when until when. Okay? This is the time interval. This is second category. And third category is the time series. We have 3 data sources. We can say the third one is abnormal. You see what I'm saying? So we can consider 3 different categories for the abnormal type of the anomalies in multiple data stream. So in this study, we, like I said before, the multiple data stream can be represented as a graph. So here, okay, we have, for example, 3 data sources, data stream, and we put 1, 2, 3, 4 different time interval, right? 1, 2, 3, 4, and then each data interval, each time. So in this case, I put only 2 graphs, okay? But actually we have 4 different graphs for each time interval. We have, in this example, we have 4, I should have put 4 graphs, okay? But anyway, in the first graph, we can find out the dependency between the data sources, data stream. Okay, for example, we have 1, 2, 3. So F, P, C. Okay, the first one is F, second one is P, and third one is C, right? So each data source represented as a node. The dependency between the data sources represented as a links, the edge between the nodes. Okay? So F, P, C, and if there is a relationship, if there is a dependency between F and C, and we measure some dependency with 0.9, we can have this kind of graph. Okay? Clear? Okay. Oops. So finally, in the last time interval, the last one, right? So you can have we can have another graph for this particular time interval. So FPC, we find out that there is a relationship between the data sources like this, and then 0.6, 0.7, 0.4. Okay? So over time, from the beginning until the end of the data source, we have several time interval, and each time interval represented as a graph, right? And over time, the graph is changing. So changing means you have a different score on the edge. Okay? So it's very natural, right? It's very natural. In the beginning of the semester, you have a friends, right? But some friends is okay until the end of the semester, right? Sometimes your friendship is changing, right? So it's something like a dynamic social network, right? We want to understand how your friendship is changing. It's very easy, right? So sometimes you fight with each other, right? You are not friend anymore, right? So this is some kind of abnormal state. So we decide when you have a new friends, when you don't have any friends. So this is a very simple example for our study. So you have multiple time series, and each data points means the dynamic graph from the multiple data streams. Very simple, but we have a very nice results. We have really surprised. I was really happy with the good results and so on. Okay, anyway, let's move to the next. Okay. I'm going to explain more details, but the main goal is only detection. So we have, for example, if we have several rooms in this building, the goal is we want to detect a fire as early as possible. How can we do it? You know what I'm saying? So some room has the sensors for the temperature, but some room has no sensors. Okay? So we collect the data from multiple sensors, and if there is a very strange patterns, then we detect the fire. Anyway, we want to explain, I will explain more details. So detecting anomalies in the early stage. Okay, so anomaly detection will be much more useful when it could be done earlier, right? Like I said, the goal is we want to detect the fire as early as possible, right? Compare with other systems, compare with other methods. So if the warning signal can be detected before the seizure, so seizure is one of the disease, brain disease. You know what is seizure, right? Seizure? Okay. So the patient can prevent the harm caused by ellipse in advance, okay? So if you have, for example, a heart attack or cancer, you need to detect earlier, right? Then they can go to the hospital, right? Otherwise, we will have a really serious problem. The fire alarm also the same, right? So in this case, due to the variety of abnormal patterns, existing supervised learning model is difficult to detect anomalies that are not learned in the past. Okay, in the training data set, you have all the data, all the information already. Then everything is okay, right? You know everything. You know all the medical knowledge. You know everything. You know, for example, temperature is going up from 20 to 30, 40. And then there is a fire. You know what I'm saying? If you have this kind of knowledge, it's okay. Right? But problem is we have no knowledge. We have only the knowledge that if the temperature is greater than 80, then this is fire. You see what I'm saying? But you have no knowledge like 20, 30, 40. The temperature is going up until you reach the threshold. You cannot detect this is fire. Yep. I'm going to explain. He said the sequence, but I'm going to explain how to detect these changes, this sequence. Okay? We are not using sequence, but I'm going to explain more details. You see, you know what I'm saying? So we don't need to wait until the temperature is 80, right? Before 80, we can detect the fires and also the cancer or heart attack, right? So the conventional methods for anomaly detection to forecast the multiple time series. This is what we want to do, right? So conventional methods is not actually efficient. We need to collect the training data set before, right? So the research problem in this study, okay, since the multiple time series combine the noise, the conventional pattern in time series cannot perform high enough, okay, for the anomaly detection. What kind of anomaly patterns can be extracted from multiple time series? So in this case, we have some kind of statistical method to identify the dependency between the time series. So we are using grandeur coefficient to decide the dependency between the time series. Second question, since the correlation among time series, multiple time series are utilized as a patterns to detect anomalies, how to model the extracted patterns for anomaly detection? Like I said, we are using dynamic graph, okay, for each time interval. So we have each time interval and we have the graph, okay? So over time, the graph is changing. That's why we call this is dynamic graph. Since the conventional model for anomaly detection are based on supervised learning method, there are some limitations for the conventional model. How to construct a model for detecting the anomalies? So he asked the sequence, Okay, from 20, 30, 40, 50, there is a sequence. Yeah, but we don't actually consider the sequence. We just consider the graph entropy. So, like I said, we have the dynamic graph, right? We have graph 1, 2, 3, 4, right? And then we measure the graph entropy. So I'm going to explain what entropy means. But if the entropy is changing dramatically, and we decide there is some events, we have to take care, right? Okay, so we are using the graph entropy to calculate the dependency between the data stream. Since the multiple time series is hard to predict, the conventional methods for early anomaly detection on time series perform low. How can we detect anomaly in early stage? So we try to integrate all the ideas into one architecture. We integrate like I will show you later, but do you know I'm going to talk about this, but in the last. But do you know about meta learning? Have you heard about meta learning? No? Okay, I'm going to explain later, okay? So we are going to propose a meta learning for anomaly detection. This is what we want to, hear, early detection. Okay, I'm going to explain later. Don't worry. What time is it now? It's 11:30. So, okay. What is the lunch time during in Vietnam? Lunch time? You have no lunch time? No. Just ask. What is the lunch time? When do you go to the restaurant? Do you have a cafeteria or restaurant in the campus? Right? Okay. Okay. I just want to manage the time because now it's 11:30 and I want to. It's 11:30. We want to. Okay. So anyway, I'm going to finish before 1 p.m. Don't worry about it. And okay, 1 p.m. Okay, don't worry. So anyway, we are going to we are now talking about anomaly detection from multiple data stream, right? So you have like a time. There's time window. Multiple data sources with different data, right? Different values. And there's a T1, T2, T3, something like this, time interval. Because you can ask the question, okay, how can we decide time interval, right? This is also a good question. I always have the same question when I explain this idea. It's experimentally decided. We test with many different cases, and we decide like in case of climate data, we decide like 1 week or 5 days or 3 days as a time interval. But in case of the fire alarm, we have to decide like a 10 second, 20 second, 30 seconds, something like this. Okay? So it depends on the application. We have to decide the size of time interval in different way. Okay? But anyway, we have the time interval like this, and like he said, we can easily apply the regression model. You know the regression? Right? Linear regression, like a 20, 30, 40, and then we can decide that the next value is 15, right? It's a regression, linear regression. We can easily apply the regression model, and then we can predict what will be the next step, right? You know what I'm saying? Yeah, okay. But of course, it's a very simple idea. course, we can use a regression model to predict the next level, okay, next step. But we are using the deep learning architecture, so we don't use a regression. We are training, we are learning the patterns from the data. Okay, so now we have x1 to 3, 3 data sources, and since we decide the time window with a blue box, okay, and all the data stream can be represented as a node in the graph, okay, x1 to 3, and the edge link between the nodes will be decided by the statistical analysis. So, okay. So in this study, the nodes represent the sensors, data source. The edge represent the dependency relationship between the sensors. Okay. So the edge from one sensor to another indicates that first sensor used for modeling the behavior of second sensors. So it means there is a relationship between the sensors. Okay. So this is the main concept of the study. Okay. So on the left-hand side, we have the multiple time series like this. Okay. We have 3 different sources, and each time interval can be represented as a graph. Okay. So we have, for example, 4 time interval. So we have 4 different graphs, okay? T1, T2, T3, T4, okay? We have different graphs. And please remember, we have studied about graph embedding this morning, right? So once we have the graph, we embed this graph into the embedding space, okay? So the results, the final result is like this, okay? So we have one. Okay, there is some mistake. We have actually n graphs, okay? So we will have this kind of result. This kind of result, okay? So here is T1, T2, T3, T4, T5, T6, right? And then if the value, the embedding result is completely different from the others, we can say this is abnormal. You know what I'm saying? It's very easy to interpret, right? This is the main concept, right? See? Any question? It's okay? Can you? Okay. So dynamic graph construction, we embed, and then we can predict what is the next level and whether the next level is abnormal or not, right? So early anomaly detection by analyzing dynamic graph of the multiple time series. This is the step 1, 2, 3, 4, right? And we already implement all the systems and the source code and the data already released on GitHub, right? So if you are interested, you can download it, you can use it. Okay, like I said, we put all the idea into one system. So this idea, this concept has been represented, implemented with LSTM, which is one of the idea from RNN, right? Recurrent neural network. So here is the graph construction. So we have the graph 1, 2, 3, 4, 5 from each time interval, right? So we use graph embedding methods for embedding space. And then we need to predict, not regression, okay? We need to predict the next level, next step by using the LSTM, right? So here we have a bi-directional LSTM, which is called bi-LSTM, right? We are using the forward and backwards, and we are trying to learn what will be the next graph, next step. So once we have the several different prediction, we decide that this prediction, this one is strange, this one is abnormal, this is normal, this is abnormal. Okay, and then we can decide, there will be fire soon. Okay, this is what we are doing. So graph construction, embedding space construction, graph prediction, decide whether there will be a normal or not, right? Okay, so this is also very interesting. So when you consider the dependency between the time series, there are many discussions already, especially in statistics, which is called spurious relationship between the data. So there are three types of dependencies. Okay, correlation, causality, and spurious relationship. When you consider the edge between the nodes, edge between the data sources. Okay, so each time series, okay, we need to find out whether there is a dependency between the data sources. We have to consider three different dependencies: and correlation, causality, spurious relationship. This is very easy example. For example, beer, ice cream, hospital temperature. If the temperature is going higher, what happens? You will eat ice cream, right? It's hot. What about beer? You will have more. You can drink beer, right? So you will have more beers. What about hospital? Hospital? If you have hot weather, hospital? No, I don't know. Anyway, the causality. What do you think the causality? Causality? Do you know what is causality? Cause and effects, right? Cause and effect. So if the temperature is higher, you will have more ice cream, more beer, more hospital, right? Spurious relationship. It looks, there is some kind of relationship, but actually, no, there's no relationship. Okay, for example, the temperature is higher, like a summer, you will have more ice cream, more beer, right? But what about the relationship between ice cream and beer? What do you think? No, it looks there is some kind of relationship between ice cream and beer, right? Because of the weather, because of the temperature. But actually there's no relationship between ice cream and beer, right? So we call this is a spurious correlation. So we have to remove it. We need to be careful when you consider the relationship between the nodes, okay? So this is what I'm trying to explain. Causality, correlation, spurious relations, we have to remove, we have to discard the spurious relationship. Only the correlation and causality for the dependencies, okay? So the next question is, okay, Professor, how to find out the dependencies between the data sources? So we are using the Granger causality test. This is from statistics, very classical idea. Of course, we can use another dependency testing, right? If you have something new, something kind of better idea, no problem. You can use another ideas, no problem. We just use the idea from statistics. So this is a Granger causality test. This is a statistical testing. You have a data stream. You find out there is some kind of causality or correlation between two data streams. And then you can find out, okay, here, causality discovery, C, X and Y, right? So if P, So the P is the value from causality testing, right? And then the P is smaller than 0.05. This is the statistical threshold, right? You can put here also like a 0.1, 0.01, depends on the situation, right? You can change it, no problem. Anyway, some statistical testing, you decide there is edge or not, okay? So, you have a statistical test and you decide there is a dependency between V1 to V0, 0.6, and V1, V2, there is a relationship between V1 and V2, 0.7, and then 0.4 between V0 and V2, right? This is a statistical test, very simple, right? Okay, so once you have this kind of graph, right? The next step is to measuring entropy. So what is entropy? Do you know what is entropy? Entropy. Information theory. How to measure the entropy? What is the definition of entropy? Do you know the stability? Stability, how stable a system is? If the system is no change, the entropy is not increasing, right? Same. But system is moving, changing, right? The entropy is increasing all the time, right? So you have a data, you have a data, right, from the beginning, from 3 different sensors, right? If all the value from sensors are same, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 10, 10, 10, 10, 10, what happened? You will have some kind of graph, but your entropy of the system is same, no change, right? You know what I'm saying? But if the data is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 10, 12, it's changing very dynamically. Your entropy is increasing, right? Okay, so we have designed that there is some kind of idea for measuring the entropy from your data, from your graph. Okay, so you have the graph V1 to 3, with 0, 1, 2, and the weights, the dependency between the nodes is 0.6, 0.4, 0.7, something like this. You measure the entropy. So the graph entropy can be measured with okay, this is a definition. How can we measure the entropy from the graph? So in the first step, we have to measure the entropy from each node. Okay, what is the entropy from V0? What is the entropy from V1 and V2? Okay, and if you sum everything, right, plus summation, okay, then you will have the graph entropy. So at the end of the slide, you will see the entropy G. G is the whole graph, okay? Is entropy V1, entropy V1, 0, entropy V2, and you will find graph entropies. Okay? Okay. So, entropy-based early detection. So, like this, we have the time interval 1, 2, 3, 4, maybe 4 time intervals. It means that we have 4 different graphs, okay? And the first one and the last one. Okay? So your graph is changing. It means that your entropy of the graph is changing, right? So in the first graph has entropy with 0.133. The last one is 0.041. This is predicted graph. You predict the next level of the graph, and then you can measure, right? Otherwise, you cannot have the early detection, right? The goal is to detect earlier the anomalies. Okay. Okay. So, like I said, graph embedding so you can apply the graph embedding ideas for the dynamic graphs over time. You have different time intervals, and you have different graphs, and you have to apply the graph embedding, and then the result is like this. Okay, so the blue one is a normal. You can decide the normal because most of the case is in the same cluster, right? With a small distance, short distance. But if you see the Tn, which is the predicted for the next step, next time, you will see, oh, there is a quite, far from the normal state. You can decide maybe this is some kind of abnormal state, right? Okay, I'm going to. Okay. So we consider not only the graph entropy, but also we wanted to consider the structure of the graph. This is a very simple example. Like we have only 3 data sources. So it means that we have only 3 nodes. It looks very simple. But if you have a 100 data source, 200 data sources, your graph looks very complex, right? Because you have 100 nodes, 200 nodes. Okay? So in this case, we consider not only the node entropy to measure the graph entropy, but also we consider the structural similarity, whether the structure looks similar or not, right? Like a structure of the graph. Okay, so the first 2 graphs looks very similar, right? There is an edge between x and y, and also edge between y and z, right? It looks similar. But the next step is there is no edge between y and z, but there is a new edge between x and z. So the structure looks different, right? And then we can decide maybe there will be the abnormal patterns for the next level. So in this case, you remember that I already explained that graph clustering, right? In the previous slides, you have many different graphs, okay? And you can apply some clustering for the graphs, okay? So in this case, you have many different graphs. You want to cluster the normal states and abnormal states. Okay. So in this case, you are applying the graph neural network to cluster. Okay. So this is optimization. We want to optimize the result because by tuning your parameters. Okay. I already shown these figures before. Okay, I'm going to skip. I already explained about the local outlier factors because we need to evaluate whether our result is good. If it's good, how good, right? If it's bad, how bad, something like this. So LOF is a standard evaluation method with other studies. So we are using this evaluation methods to compare with other methods. I'm going to skip. Okay, like I said, we decide, it was very hard to decide the size of time window, right? So like I said, climate change, climate weather, data, it's very long. We have to decide the size of time window is 1 month, 1 week, 10 days. It's not easy to decide. So that's why we test with many different cases to find the optimal size of time window, time interval. So this is the results. So in this case, we had the data from Chinese climate data and Korean climate data. So in this case, 60 days for Chinese weather and Korean weather, we decide 40 days will be the best size of the time interval. Okay, I want to skip. Yeah, skip. Conclusion. I'm not so sure how many of you are interested in this study, but to be honest, personally, this is kind of a new approach. Nobody tried to analyze the climate data for anomaly detection. This is kind of new direction. That's why I'm pretty proud of this result. And we find out that, in Vietnam also climate change is important issue, right? Every day the weather is changing. Yep. Yep. Thank you for the comments. So everybody knows the climate is changing, right? The temperature is going higher. The iceberg on the north and south is melting. The sea level is higher. We know, right? But from the data, from the data, we have a lot of weather data. We know that the temperature is higher. It's obvious, right? But in my point of view, we want to understand our ecosystem is not stable anymore. You know what I'm saying? Because entropy of the data is changing. It's not stable anymore. That's what I was proposing in the paper, in the study. Maybe you can ask me how to evaluate our study, our result is reasonable, right? So, okay, this is the publication, my publication with these ideas. I have 7 journal papers. We have tried. I'm looking for the slide for the evaluation. Okay, I didn't prepare the slide. What do you think about the strange, abnormal weathers? How can you define if the weather is abnormal? How can we decide? How can we define? So today is normal or abnormal? The weather. How can you decide? So I want to ask you, okay, whether it's abnormal or normal?
The weather is seasonal. So in the middle of the winter, if the temperature is higher than 30 degrees, then it's an anomaly.
Okay, that's your definition. Another idea is how can we decide whether today's weather is normal or abnormal? How can you think? No idea? Every day you just leave, oh. Yeah. He said he can compare the temperature with the previous years, right? Last year, 2 years ago, 10 years ago, 100 years ago, the weather, what is the difference between the weather, right? In the past. This is exactly the scientist on the weather is working. But we have another ideas. We want to find out the relationship between the weathers. For example, in our study, we are using so many different weather data. not only the temperature, but also humidity, but also sea level, but also the rain, how much the rain we have, right? So we have like more than 10 different data sources, right? You understand what I'm saying? Okay? So 10 years ago, 20 years ago, 100 years ago, the humidity, temperature, sea level, any weather data, they have a very stable relationship, dependencies. If the temperature is higher, the humidity is going down. It's a very obvious, right? In physics. But this rule is not available anymore nowadays. So we count each day. We try to measure the abnormal scores, because we need to decide the today is abnormal or normal. Okay? So this year 2023, 2022, 2021, okay? Last year, 2 years ago, 3 years ago, every year we count number of strange weather days. Okay, I will explain again. Every year we count the days with the abnormal weather. Make sense? So 10 years ago there was abnormal weather with the 10 days. Okay? But now, like more than 100 days. Our system, our ecosystem, the weather system is very, very unstable. This is what I was proposing in the paper, in the study, right? Make sense? So number of abnormal weather is dramatically increasing nowadays. By compare with 20 years ago, 30 years ago, 40 years ago. So we have used with the Korean weather data, Chinese weather data, Japanese weather data, all the same. We have all the same results. So that's what I want to discuss with you. Yeah, this is 12. Now this is end noon. Can you open the last one, 5? Okay, so this is the last part. I want to finish it within 15 or 20 minutes. Okay, so now I want to talk about application and my experience. This is another paper, another study that we have tried to use the anomaly detection for traffic. So here everybody knows that edges, you know, edge computing, right? So all the vehicles are nowadays connected vehicles. Do you know connected vehicles? V2X, vehicle to everything. No? IoT, Internet of Things. So we in the future we think that there will be a lot of vehicles. Most of vehicles are connected. They are sharing the data. They are communicate with each other. They are okay. I'm moving 20 kilometers per hour from west to east, or my destination is PTIT, something like this. We are sharing the information between the vehicle, right? So in this case, we want to use dynamic graph embedding for anomaly detection. So here, anomaly detection means understanding the traffic condition, whether there's a congestion. You know congestion. There's a lot of car, high traffic, so you cannot move. So we want to detect the traffic congestion by using these ideas. So all the car on the street, all the car on the street sharing the data, and this is some kind of node, right? You remember that we have a dynamic graph. Each node is a data source, data stream. Okay? So in this case, all the vehicles are nodes. Okay? So all the nodes are sending the information, my speed, my destination, my condition, you know. So by collecting the data from vehicles, we make some dynamic graph. Okay? If there is an abnormal states, there will be some problem on the traffic. Okay? Make sense? So we try to use this idea for simulation because there is no actually real connected vehicle yet. This is just a research purpose. The people want to develop these ideas in real world in the future, not now, right? So we are using some simulators, which is called SUMO, S-U-M-O. You can Google and you can download some simulators. Anyway, there is a simulator called SUMO, and we can put some streets. Okay, it's the street in Seoul, Gangnam area, and you will have this kind of street, and then you can have some synthetic data to have some simulation. And then we will automatically decide that, oh, there will be the traffic congestion. You have to go another way because there will be the congestion. Okay? This is idea. Another one is EEG. I already mentioned several times about brain waves. Okay, so you know the Alzheimer, dementia. If you getting older, your brain is working well, not working well. So your memory has some problem. You forgot. This is called dementia. So there's two types of dementia: Alzheimer and Parkinson. Okay, there's two disease. But anyway, it affects your brain. Okay, your brain has a problem. Okay, so we put some sensors. Okay, so this is called the EEG. Okay, EEG, and we have a data source like this: 1, 2, 3, 4, 5, 6, 7. Right? No, 8. In this case, we have 8 channels. So it means that you put sensors in your brain with the 8 sensors. Okay, so it depends on the system, but sometimes it's a 16. Sometimes it's 32, and so on, and you will have this kind of EEG data. So in front parts of your brain, you have alpha signal, some other parts, beta, gamma, you know, this kind of signals from your brain. So we have exactly the same idea, dynamic graph embedding with the EEG data. Okay? And then we predict, okay, this patient will have a seizure soon. Okay? And then we put this idea in this paper. Okay, climate change, the final example, final application. So, like I said, not only Vietnam, but also any countries on Earth really, big problem with the climate change. So we have more rain, the temperature is more higher, and we have a lot of floods, we have a lot of deserts, right, in Africa, in China, right? That's a really big problem. And we want to solve the problem with the AI. Okay, so how can we solve? Okay, not solve, but use AI to understand the climate change. So basically, most of the AI people are using image recognition for like this. Okay, so this is from USA. They want to understand whether there will be a hurricane in Florida. So they are using this kind of radar image and automatically detects there will be the hurricane soon. So this is how it works. This is basically the CNN, the convolutional neural network, to understand the hurricanes. But like I said, in our study, in our system, we want to apply the anomaly detection to understand the climate change. So we have a lot of weather data from China, from Korea, from Japan. Of course, maybe if we have some chance, maybe we can get some data from Vietnam weather. We can test. So in this case, we consider the spatial and temporal dependencies. Okay? So the main idea is to put the graph embedding the same idea for measuring the anomaly score in each weather condition in each day. Okay? So I will show you some example. This is what we have developed. Here, this is Korean, the map of the Korean cities. So, like I said, we want to detect today is abnormal or normal, right? This is what we want. And like I said, we already find out that we have more abnormal days compared with 10 years ago, 20 years ago, right? But as a next step, what we have to do, we try to consider spatial and temporal dependencies into one system like this. So we want to find out which city has most abnormal weathers in Korea. You know what I'm saying? So in Vietnam, for example, Hanoi, Ho Chi Minh, Da Nang, Hue, Haiphong, and we have many cities in Vietnam, right? And you want to know that which city has most abnormal weathers in Vietnam. Make sense? So we have this kind of system to explain. Okay, Seoul, for example, Seoul, Busan, we have Busan, Yeosu, Gwangju, something like that. We have several cities. And then we want to explain to the people, okay, your city has the most abnormal weather days in last year. You need to be careful. Your city is strange. You know what I'm saying? And also, I'm living in Seoul. For example, I'm living in Ho Chi Minh City. I want to find out when was most abnormal weather. You know what I'm saying? Yesterday, last year, 10 years ago, when was the most abnormal weather? Okay? This is the system, how the system is working. So this is only for curation and explain your city, your country, the days. Okay? Maybe okay. And I want to share my plan from this system. What will be the next system? So we have the data from we have the result from China, we have the result from Korea, we have result from Japan. We want to compare the cities in each country, in different countries. So the Seoul, for example, Seoul in Korea is very similar with the Shanghai in China. You see what I'm saying? So, I mean, in terms of the abnormal weathers, because the people in government, people in big company, they want to develop the cities, which is called urban design, urban planning. So if you have a new apartment, new street, new city, it's really, really important to decide the place, right? How to develop the cities, right? So you always need to compare with other cities. Okay, this city has a very abnormal weathers, okay? And why? You see, understand? If there's a new city, but there's no abnormal weather, the weather condition is still same, and why? Okay, we need to follow, we need to use the same policy with these cities, because we don't want to make any changes, right? I hope you can understand what I'm saying, okay? Okay, the last part, okay, so I want to finish it in 10 minutes. Open issues, so the first part is anomaly localization. Okay, like I said, in the building, okay, PTID, okay, for me, this is my personal opinion. PTID is a relatively small campus, right? If you see really huge, really big buildings, how can we detect the fire? You put a lot of sensors, right? But number of sensors are not enough to detect the fire efficiently, right? So in this case, anomaly localization is to detect the location of the fire. Okay? Okay, you have a lot of money, you have a lot of resource, you have a lot of sensors. You can put all the space with sensors, right? If you are rich. But you are not rich, so you have to find out that the optimal number of sensors. Sometimes it's not easy, right? You have to decide. Yep. Yep. Yes, exactly. Exactly. Yep. Thank you. Right. So like he said, we have to find out the location and when the fire happened with a limited number of sensors in a very big building, right? It's very practical. And for example, if there is an accident, you have okay, for example, in the highway or in any street, there is a lot of congestion, right? Suddenly, because of the accident, right? But if you have several sensors around the street, you can find out where the accident happened. Okay, makes sense? So we want to apply our idea to localize the anomalies. This is the idea. I have several students in my lab, and we are still working with this. Hopefully, we will release the system, release the data, and also the paper, right? For this. Maybe this is okay. This is the last slide. I already mentioned many times. The early detection is really important. This is critical. This is the main issue of the anomaly detection. So you have a data, for example, 10 years data, 20 years data. You want to find out which date is abnormal. You have a data from the building, right? Temperature data. Okay? But most of the research, most of the case is detecting the abnormals after the events, right? You have a fire here, okay? You didn't have any alarm, right? After the fire, you try to understand, why the system didn't alarm the fire, right? This is how it works mostly. But in this case, now people are talking about the prediction and detection of the anomalies earlier, before the events. So yesterday I talked about smart factories. You have many machines, many people are working in the factory. If there is a problem in the machine, they will have a lot of, cost. All the factory must stop. Okay? You know what I'm saying? So the factory must detect, predict, okay, there will be the problem. I need to replace. Okay? Then we can save the money. We don't need to stop the factory. So that's why we have to study. That's why we have to focus on detecting the anomalies as early as possible. This is what I was sharing as an open issue. So is it possible to detect anomalies as early as possible? This is the question, open question. Maybe not only for me, for you, if you're interested in this topic, hopefully you can focus on this topic. Thank you for your attending. I want to close. Maybe some of you are boring. Maybe this is, actually I was sharing my experience. I hope to have some blackboard and writing my experience, having some practice and some writing some code, but it was a little bit different than I expected. So maybe some of you are boring, but some of you are interested in my topic, and I hope you can have some insights, okay, with the deep learning or anomaly detections and so on. I had like 2 or 3 hours, 2 or 3 hours yesterday. Today also 2 or 3 hours talk. It's not enough. I'm pretty sure that it's not enough. You need to go another paper, another website, another textbook to learn more. Okay, so I just share very basic concepts. Okay, so I hope you have some chance to study, and I hope to see you again somewhere. Hopefully. Thank you for your listening. Thank you for your attending. Thank you very much.